Hello again. Let's continue with chapter 2, and we're going to get into the concept of resonance today. I don't know why my video is still getting lost, so we'll try again to see if it will continue with my webcam after I start my screen sharing for my iPad. It is being a little wonky, so we'll find out. All right, let's take a look at page 3 of our lecture notes. Let's come back to another example of a Lewis structure. This one's maybe a little more complex than the examples we looked at before. How about the structure of nitric acid? And actually, this is a case where the condensed formula, the way it's usually written, HNO3, is not really a good representation of its structure, because really it should be written as HONO2 to represent its connectivity. So in other words, the hydrogen atom in nitric acid is actually attached to an oxygen, and then the nitrogen serves as the central atom for the other, for all three oxygens are attached to that. So with that skeleton, see if you could draw the complete the Lewis structure of nitric acid. Again, if you want to pause the video, that would be a great exercise for you to do. I will continue drawing it. Remember, the goal is to fill as many octets as possible. And so let's see, adding 2 lone pairs to the oxygen would be pretty good. And maybe this top oxygen, again, 2 bonds, 2 lone pairs, so I can add a pi bond here. But all of a sudden, when I do this, I find that my nitrogen now has a filled octet, and this last oxygen can't have 2 bonds like it wants to. Instead, it's going to have 3 lone pairs to fill its octet. And so if you do the math for the total electrons that nitric acid should have, this is exactly the number that you would get. And unfortunately, that means we have some unusual bonding patterns, and we're going to have to check for formal charges. So what do you think? That nitrogen with 4 bonds, 1, 2, 3, 4, it's missing an electron, so this is an N+. And this oxygen is also unusual, so we'll check. 1, 2, 3, 4, 5, 6, 7. It has 7, but oxygen only wants 6, so this is an O-. So this is what nitric acid looks like. Even though the molecule as a whole has no net charge, it's impossible to draw it without these formal charges. We have an N+ and an O-. Just a reminder here that a very common solution that students come up with here for nitric acid would be to have a double bond to both oxygens, okay? And at first glance, that looks like it might be nice because we have avoided those formal charges, but that's not true, because what's the problem here? This is another impossible structure I've drawn. It's impossible because we can't have 5 bonds. No nitrogen with 5 bonds, because that would be a total of 10 electrons. You can't have more than 8 electrons. Okay, so with everyone having a filled octet, this is the structure you get. But if you drew this structure, you might have said, well, wait a minute. What about the possibility, instead of drawing a double bond to this top oxygen, couldn't I draw a double bond to this side oxygen? And I can. That would be another possible Lewis structure to draw, another valid Lewis structure, where I have the double bond in this direction and the single bond with the O- up top. And of course, that would still be an N+. So how do we describe it when we have more than one Lewis structure we could draw for a given compound? These are described as resonance forms or resonance structures. They both represent nitric acid, and we use a very special arrow to connect, to point from one resonance form to the next. We use this very special arrow. It's a single line with arrowheads on either end, and sometimes we put a little bracket around this whole thing to signify as well that it's resonance forms. And so what does it mean when you have resonance? Here's some descriptions of resonance. You'll see this in section 7 through 12. That, again, a huge part. This is the most significant part of chapter 2 is learning all about resonance. So what it says here is that if you can write more than one Lewis structure, that means actually none of those Lewis structures accurately describe the actual compound. The actual structure is some kind of hybrid of all these possible Lewis structures. It's not flipping back and forth. It's not sometimes this and sometimes this, right? So we're not looking at an equilibrium here. It's actually not this or this. It's something in between, right? So what does that resonance hybrid look like? The actual structure, the best representation of nitric acid would show a partial double bond between both from nitrogen to both oxygens. So the real bond, it's not a single bond, it's not a double bond, it's somewhere in between. It's like a partial, like a bond and a half. Okay, and the nitrogen has a positive charge, but the negative charge is delocalized. It's shared between both oxygen atoms. So the way we represent that is we use the delta symbol. The delta symbol, remember, represents partial, the word partial. So we have a partial charge on each oxygen, a partial pi bond to each oxygen. That's what the hybrid looks like. Okay, but that's a really ugly structure. There's not much we could do with it. So we don't draw the hybrid. We just draw a discrete Lewis structure and we say, well, it's not exactly this, but this does represent it to some extent. Okay, now something that's really important about resonance is that it always represents stabilization. It's always a good thing. Okay, it's great to have resonance. Anytime we have resonance, that is good news. Okay, because what it means is the hybrid is actually more stable than any of the other Lewis structures we can draw. Resonance means stabilization. We describe that amount of stabilization as the resonance energy. Okay, now kind of a more advanced topic that we're going to be coming back to down the line is that what we're actually doing in kind of converting this resonance structure to this resonance structure. What is the relationship of those two? What you see is that we've changed the location of the pi bond and we've changed the location with the lone pairs, and that's what resonance is. It's the redistribution, the delocalization of pi bonds and lone pairs, pi bonds and lone pairs. Okay, it's not sigma bonds moving. Sigma bonds are frozen. No atoms are moving. The atoms are frozen. The bond lengths, the bond angles, they're all frozen. All we're doing is showing a redistribution of the pi bonds and lone pairs. And of course, there can't be any change in the overall charge because we're just shuffling electrons around. We're not adding any electrons. We're not removing any electrons. So our overall charge can't change. Okay, so let's take a closer look at some resonance and start to get a feel for what does good resonance look like? How can we identify that? How can we look for that? Okay, so not all resonance structures are created equal. Okay, some are kind of look better. Some are therefore better contributors to the overall hybrid. So let's see what makes a resonance structure look good versus looking not so good. Okay, so number one, as always, the holy grail, the ultimate thing we're looking for in good looking Lewis structures is the maximum number of filled octets. We always want to try and have everyone with a filled octet. And the more filled octets we have, the better the Lewis structure. One way you can maybe identify that there's more octets is there's more covalent bonds because more electrons are being shared and therefore more likely to have filled octets. So let's take a look at two resonance forms. So we have this resonance structure and we have this resonance structure. So these represent the same compound. Again, here's the hybrid. The hybrid has a partial double bond between the carbon and the oxygen. It's not really a single bond. It's not really a double bond. Okay, and the positive charge is delocalized. Let's do that. That language is really important to get a feel for. So the positive charge is delocalized. So it's not, to be localized means it's in one location. To be delocalized means that it's in multiple locations. So it's delocalized over 2 positions over both the oxygen and the carbon, because in one resonance structure it's on the carbon, and another resonance structure it's on the oxygen. Okay, so and this is one of the skill builders, is being able to draw the hybrid resonance hybrid given resonance structures. Okay, now when I compare these two, I see that this one is missing an octet. Do you see this carbon has only 3 bonds? It has a total of 6 electrons around it. This has a carbocation in the structure. So this is missing the carbocation, the carbon with a positive charge is missing an octet. Where in the next one, where we have the electrons being shared as a pi bond, this carbon now has a filled octet, and the oxygen also has a filled octet. So this is the more important, this is the better resonance structure. Now, the next skill we're going to take a look at is how can we maybe convert this resonance structure into this resonance structure. What we're going to be using is curved arrows to show how the electrons are changing positions. Okay, and this is a skill that we're starting here. We're going to continue in chapter 3 and beyond. We're going to be using curved arrows to show electron movement for the entire year of organic chemistry. And so when I compare these two structures, you can see that I had 2 lone pairs and now I only have 1. And I also have this new pi bond. So what does that mean? It means that these two electrons, one of the lone pairs here is gone, and they're now being shared as a pi bond. So the way we show that electron redistribution is we show a curved arrow starting at the lone pair and pointing to the bond. And what the curved arrow shows is these electrons, they started here and they points to the new position of those electrons. So that curved arrow shows how we can convert the first Lewis structure into the second Lewis structure. All right, so goal number one, always, always, always try and fill as many octets as possible. All right, what else can we do? Sometimes we're going to have formal charges in our Lewis structures. If we have a resonance structure with no formal charges or maybe fewer formal charges, that's going to be the better contributor. So here's an example where we have this as a Lewis structure that has no formal charges. This one, and then these others also now have a plus and a minus. Okay, so this is the best one. This is the one that the hybrid, the actual structure looks mostly like this. This is the biggest contributor. This is the biggest contributor to the hybrid. Biggest contributor to the hybrid. So overall, this is kind of the best picture. Sorry, my words floated a little bit. This is the best picture of what this molecule really looks like. Okay, but it does have some additional resonance contributors. This one is not quite as good because it has 2 formal charges, and this one is the least important. Can you see the difference between these two on why that third one I'm saying is the least important compared to all 3? Because it still has a plus and a minus, but what are we missing here? Aha, we have a missing octet once again. Okay, so this one has no octet at the carbocation, and so that's the one that is the least significant of all 3. Okay, now let's get a little more practice with our curved arrows. How can we show how the first structure got converted into the second structure? Do you see the difference in the electrons? This lone pair is gone, and where is it? It's now moved over to become a pi bond between the carbon and nitrogen. And as I formed this bond, I also broke one of the pi bond in the CO double bond. And where did those electrons go? They moved up onto the oxygen. So 2 curved arrows show the electron redistribution. We're just showing a formality, trying to keep track of our electrons. How can you convert the first structure to the second structure? So we use 2 curved arrows for that. Okay, do you see how we would convert the second structure to the third structure? How are the electrons moved? We are getting rid of the pi bond, and where do those electrons go? They are going to be sitting on the nitrogen. So the pi bond goes back to being a lone pair on the nitrogen. So curved arrow formality. All right. Now, if you already have a charge, sometimes we're dealing with a compound or an ion that already is charged, then we're typically not going to create new charges. Our goal in that case is to see, hey, how many different places can we move that positive charge? Or can we move that negative charge? We want to delocalize it. We want to delocalize it as our goal if we already have a charge. This one didn't have any charges, so as soon as we move electrons around, we automatically get some charges being formed. Okay, what else can we look for to evaluate the quality of a resonance structure? All other things being equal, so let's say we have the same number of octets and so on. The structure with a negative charge on the more electronegative atom would be the better Lewis structure. So negative charges like to be on more electronegative atoms, positive charges like to be on less electronegative atoms. So if that's the only difference between two resonance forms, that's what we can use to rank them. Okay, so when we look at this resonance here, this CO double bond can have resonance, and the resonance is gonna have is where the pi bond moves where it moves to the oxygen to give me an O minus and a C plus. That is good resonance because the oxygen is more electronegative, so it's better with the negative charge. Okay, what would be unlikely is if we broke this pi bond and moved the electrons to the carbon instead. Why? Because that gives me a carbon with a negative charge. That's not so happy. And it gives me an oxygen missing an octet. That's really awful for an oxygen, for an atom that's so electronegative. Remember, oxygen is the second most electronegative atom in the periodic table. So that's how we would recognize that this resonance is very unlikely. And we would want to do this type of resonance instead. So the negative charge is going to want to be on the more electronegative atom. That would always be good news. All right, and finally, sometimes when we compare two structures, we don't find any difference. They have the same number of octets, they have the same number of charges, the charges are on the same elements, and so in that case, it's okay that you don't find a difference. We describe them as being equivalent. We describe them as being equivalent. This is called the allyl carbocation, and it has two resonance structures, and they're equally important. They're equally important. They contribute equally to the hybrid as well. How could I convert this first structure into the second structure? How could you describe using curved arrows? How can you show where the electrons have been redistributed? And it's simply this pi bond. This pi bond is just shifting over into a new position. So it shifts from the left-hand side to the right-hand side. Okay, and as a result, this carbon used to have 4 bonds. Now it has only 3 bonds. So notice that the charge ends up moving as well. Okay, but we're not showing, our curved arrow doesn't show the charge move. Okay, remember, our curved arrows only show electrons moving. They don't show charges moving, they show electrons moving. As a result, when we evaluate the next Lewis structure, the next resonance form, that's when we say, oh, here's a positive charge, here's a negative charge, and so on. All right, let's see if we could get practice. What would the resonance hybrid look like for this? We're going to see this in Scale Builders 5 and 6, drawing Lewis structures and drawing resonance hybrids. What do you think? So between the first 2 carbons, is it a double bond or is it a single bond? Actually, it's somewhere in between, right? It's a partial double bond. It's like a bond and a half. And same thing between the second 2 carbons. It's somewhere between a single bond and a double bond, so we draw a partial double bond there as well. And where are our charges located? We have the third carbon has a positive charge character. The first carbon has a positive charge character. So how do we represent that in the hybrid? We represent that with a delta plus. The first and third carbons both have partial positive charge. In fact, they both have exactly a half of a plus positive charge because they both contribute equally. All right, so what else do we want to be able to do then if you're going to be drawing resonance forms? How can you identify when resonance is going to happen? Turns out that there's a handful of patterns that we're going to keep an eye out for that are really important in identifying that resonance is going to happen. Okay, so here's a few things to look for. One of them can be described as an allylic lone pair when we have a lone pair that's next to a pi bond, lone pair next to a pi bond. So the word allylic means next to a pi bond. So notice this, we have a lone pair and it's not on the double bond, right? It's not on the double bond. It's on the position immediately adjacent to the double bond. So this is called an allylic lone pair. Every time you have an allylic lone pair, you're going to have resonance. It's going to be two curved arrows. It's going to be two curved arrows. The lone pair becomes a pi bond, and then the pi bond becomes a lone pair. Lone pair, the lone pair becomes a pi bond, and then the pi bond becomes a lone pair. Always two curved arrows. And what does the resulting structure look like? It now has a negative charge. It has a lone pair on the third carbon. And what about the negative charge? This carbon is now neutral because it has 4 bonds, but this carbon now has the lone pair. So it has 1, 2, 3, 4, 5. There's the excess electron density. So our negative charge has in fact moved to a new position. Allylic lone pair resonance. All right. Another possibility is to have in the allylic position a missing octet, a vacancy or a missing octet. When are we gonna have that? Typically when we have a carbocation is the most common way we're gonna have something that's missing an octet. So this carbon, there's only 6 electrons here total. That's a vacancy. That is missing an octet. That means it can handle having electrons add to it, and that's exactly what's going to happen. This pi bond is going to shift over to the other side to fill in that vacancy. Actually, we just saw an example of this on the previous page. That's called an allylic carbocation. Every allylic carbocation has resonance. We use that one curved arrow, and do you see where the positive charge is now? This carbon now is the one that has only 3 bonds because we just took the pi bond away from it. So there's our carbocation. Allylic carbocation. Okay, and then finally, another pattern we'll see pretty often is if you have a pi bond that's between 2 different elements that have different electronegativities. Okay, and that resonance we could describe as a carbonyl-like resonance. A carbonyl, the word carbonyl is how we describe a CO double bond. A CO double bond is called a carbonyl group. So this is resonance that every carbonyl has, and anything that's kind of similar to a carbonyl. Okay, and here we have a carbon and an oxygen. Who's more electronegative? Who's more electronegative? Certainly it is the oxygen that's more electronegative. So what happens with this resonance is the pi bond breaks and the electrons move to the more electronegative atom. The electrons move to the more electronegative atom. So this oxygen now has 3 lone pairs. And do you see the formal charges that will result from this carbonyl-like resonance? That top atom, the oxygen, now has a negative charge, and the carbon has a positive charge. So every carbonyl can do this kind of resonance. Now notice, I wouldn't expect this resonance to happen to any large extent for a carbon-carbon double bond, right? Let's make this a CH2 and a CH2. Let's just make this a complete atom here. I'm sorry, complete molecule. Okay. I wouldn't expect this resonance to happen because that's going to give me a C plus and a C minus. Neither of those is good, right? I mean, the C plus is okay, but carbon doesn't like having a negative charge. So this is unlikely. So it's only when we have 2 different elements that have different electronegativities. There's nothing drawing the electrons toward this carbon, or this carbon, and so so an ordinary carbon-carbon double bond, we wouldn't expect any significant resonance, but a carbon-oxygen double bond absolutely does have significant resonance. Okay, so those are the main patterns we're going to look for. Actually, the opposite of this one we could point out just an FYI, if we had an atom with a lone pair next to a carbocation, a lone pair adjacent to a carbocation, this is kind of the opposite of the carbonyl resonance. Do you see how this would have, there's another resonance form I could draw for this. I have an atom with a vacancy. He's missing an octet. Right next door, I have a lone pair, someone who could fill that octet. So sure enough, I would expect that lone pair to come back in and be a pi bond. So just like if we had a carbonyl, we could do resonance forming a carbocation, drawing a carbocation, or if you had a carbocation next to a lone pair, we could bring that lone pair back in to be a pi bond. So that's kind of related to the carbonyl. We're going to see some patterns like that too. So there's two ways that we can stabilize a carbocation, that we could delocalize a positive charge. If you have a pi bond adjacent to it, that can shift over and fill in the vacancy. Or if you have a lone pair adjacent to it, that can shift over and fill the vacancy as well. Okay, so those are the types of resonance that are going to answer the questions in chapter 2 and beyond. We're going to be seeing resonance play a role over and over and over. So it's such an important topic. It's such an important concept. There's another really important type of resonance, but it's not going to answer any questions right now. In fact, we're not going to see this until Chem 350. So, sorry, 3150. And that's when we look at a molecule like benzene. Benzene has a 6-membered ring with 3 pi bonds. And when you have this kind of structure, what can happen is you can shift 1 pi bond over, which forces this pi bond to shift over, which forces this pi bond to shift over. And so what can happen is we can relocate the position of all 3 pi bonds and put them in different locations within the benzene ring. This molecule is called benzene, and benzene has resonance that's known as aromatic resonance. Aromatic resonance. We're going to study aromaticity when we get to second semester organic. Okay, and so these pi electrons are totally delocalized. They're totally delocalized. They're totally spread out. And the hybrid, what does the hybrid of benzene look like? Sometimes it is represented with just a circle on the inside of the ring, representing all those 6 pi electrons just constantly being in different positions. And sometimes you may have seen something like this represented in line drawings and so on. And so if you ever see that circle, that's what that means. It just means that you have 3 pi bonds in between. So benzene does have benzene resonance. It's like I said, we're never going to be invoking it. We're never going to be working with it. We're just going to kind of ignore it for now. And we'll talk about in Chem 3150, we'll explain why it's so special, what makes that resonance so very special. All right, so let's take a look at an example where we look for resonance, and then we rank the resonance forms that we have to see which one is the best contributor, which one's the second best contributor, and so on. All right, so first of all, let's fill in any lone pairs to make sure we have all of our electrons shown before we start shuffling around electrons. Remember, that's what resonance is, shuffling around lone pairs and pi bonds. So every oxygen has 2 lone pairs, every nitrogen has a lone pair, neutral nitrogen, right? 3 bonds in a lone pair. So what are some patterns that we can see? Maybe you see that we have allylic lone pairs. We have allylic lone pairs. We have a lone pair that's adjacent to a pi bond. We have it over here. We have a lone pair over here that's adjacent to a pi bond. So those are a couple patterns we can look for. Or you might say, oh, you know what? I have a carbonyl. I have a carbonyl that has resonance. So I could do that as well. I can think of that kind of resonance pattern as well. So let's it doesn't matter which one you start with. We're going to explore them all eventually. Let's start with the allylic lone pair with the nitrogen, just as one place we could go. There's my pen. So what would that resonance look like if we wanted to use the lone pair on the nitrogen? Remember that is always two curved arrows. The lone pair becomes a pi bond, and the pi bond becomes a lone pair. Lone pair becomes a pi bond, and then the pi bond becomes a lone pair. So I can redraw the electrons as a result of those two curved arrows moving those 4 electrons. And we're going to have some formal charges as well, right? So we have some oxygens. We have a positive charge. Sorry, we have a positive charge on the nitrogen and a negative charge on the oxygen. Okay, and we can furthermore say, okay, I want the oxygen instead of that lone pair. I could use the oxygen lone pair. Or again, now I could say, hey, you know what? I see something that's a carbonyl like. That's carbonyl like. I have a pi bond between 2 different atoms. So let's do that resonance next. Say, okay, I want that lone pair to I want that pi bond to just move to the more electronegative atom. So now it's on the nitrogen. Okay, and when I move that pi bond, where does my positive charge end up? I know I still need a positive charge somewhere because the molecule overall has to be neutral. It can't have any net charge. So now it's my carbon that has the positive charge. 1, 2, 3, where carbon wants 4. Okay, and then there's going to be a 4th resonance structure. The 4th resonance structure was if I had used this oxygen lone pair to do the allylic resonance. If I did that from the beginning, that would be good. Or how can I do that now? I can say, hey, I've got a lone pair and it is next to this vacancy. It's next to a carbon carbocation. And so I could bring that pi bond in, that lone pair in to be a pi bond. So when we think about all the different ways to move our lone pairs and pi bonds, there's actually these 4 options. These are my 4 options. All right, now there's no other patterns that I can think of. If I think of, okay, oh, look, I have another allylic lone pair. I have another allylic lone pair. So I could do lone pair becomes a pi bond and pi bond becomes a lone pair, but that's going to bring me back here. Or if I say, hey, look, I have something that's like a carbonyl and I could just break that pi bond, that will bring me back here. So any of the other patterns we've explored are all going to bring us back to one of these 4 structures we've already drawn. Okay, now, which one of these 4 are is the best? Is there one that stands out that looks much better than all the others? I think the first one, the very first one is number 1. Is number 1 because it has no charges. Right, it has no formal charges, so that stands out at me. It also has full octets. Every atom has a full octet. So that's the best looking Lewis structure. That's the best contributing resonance structure. The best contributor. The biggest contributor. In other words, the hybrid of this structure, the hybrid looks mostly like this. It mostly looks like this, but it has a little bit of this characters of these characters as well. Okay, now is there any one of these that looks the worst? That looks the worst. Are there any missing octets? That would be something that would make it a very unfavorable Lewis structure. Right here, we have a missing octet. Sure enough. So our missing octet, that makes this one number 4, the worst, because it has a missing octet. All right, so now when we compare our last 2, they both have a plus and a minus. They both have all filled octets. So what's the only difference between them, and which one would be better? They both have an O minus, but where the positive charge is located, that's the only difference between these 2. So if I'm a positive charge, do I prefer to be on a nitrogen or an oxygen? Where would a positive charge be more stable? Remember, a negative charge would want the more electronegative atom, oxygen. So a positive charge wants the less electronegative atom. So that is this one. This is our number 2. And that's because N plus is better than O plus. Why? Because nitrogen is less electronegative. So this one is our number 3 resonance form. So drawing resonance forms and ranking resonance forms, that is going to be another couple skill builders that you can get. And notice how often we're using our formal charge math. We have to be just so good at that and ready to do it, calculate it in our heads, calculate it very quickly, because we're going to have to do it every single time we draw a Lewis structure. We're going to have to check for those formal charges. All right, so that's a good stopping point for our resonance forms, a couple skill builders to work on, 7 and 8. And then there's some other in-chapter problems. Remember, the skill builders you're going to find those as you're reading these sections of Klein. But some problems are also they don't have a whole skill builder built around them. They're instead just described as conceptual checkpoints. So problems 18 through 25, those in-chapter problems, are called conceptual checkpoints instead, but you'll find those in Wiley Plus as problems to work on. All right, we'll finish up chapter 2 in a third lecture in just a bit. I'll see you then.